Imagine a safe so strong that it would take the most powerful supercomputer on Earth 10 septillion years to crack. That's a 10 followed by 24 zeros, roughly a trillion times longer than the universe has even existed. Now, imagine a device smaller than your palm opening that same safe in under 5 minutes. This isn't a scene from a sci-fi movie. In December 2024, Google's Willow quantum processor did exactly that. It didn't just break a record, it broke the fundamental logic of how we keep the world's secrets. While we're all distracted by AI chatbots, a silent countdown has begun toward a moment known as Q Day. That is the day every bank account, every government secret, and every private message on the planet becomes an open book. But here's the kicker. The danger isn't waiting for 2029. It has already started. Our entire digital world is built on a mathematical lie. We assume that because a problem is hard for a normal computer, it is impossible to solve. Your banking and private data are likely protected by RSA or Diffie-Hellman encryption. These systems rely on the difficulty of factoring massive numbers. A classical computer has to guess every possible combination one by one. It's like trying to find a specific needle in a haystack the size of a galaxy.
It's branching as expected.
Good, let it run. The network is stabilizing. Let's push for full convergence.
Processing at 87%. The branches are aligning perfectly.
Monitor for any anomalies in the final factoring stage.
Quantum computers don't play by those rules. Using something called Shor's algorithm, a quantum system can find the answer in polynomial time. Instead of guessing sequentially, it uses the weird physics of the subatomic world to see all paths at once. A billion-year task for a supercomputer turns into a 10-minute job for a quantum chip. This means that once a stable quantum computer is built, modern encryption is trivially broken. You might think we're safe for now, because these computers are still in labs. You'd be wrong. There is a strategy being used right now called Harvest Now, Decrypt Later. Adversaries and nation-states are currently sniffing and storing vast amounts of encrypted internet traffic. They are collecting your data, military secrets, and government strategy documents today. They can't read it yet, but they're waiting. They are building a massive digital library of secrets, just waiting for the day they can turn the lights on. For years, the experts told us this was decades away. They said we would need 10 million qubits to break a standard code. But the timeline just shifted. Google researchers recently found a meta-program that makes the algorithm 20 times more efficient. Instead of millions of qubits, they now estimate we only need about 500,000. Some startups are claiming they could even do it with 26,000 qubits.
worse. But look at the right, it's scaling cleanly.
Yes, the stability is holding.
A breakthrough, let me see the chip. This changes everything. Here it is. The new chip is handling the noise perfectly. Incredible, the scaling is so
But
clean.
why is the Willow
did it.
chip
This is the
such a
breakthrough we've been
game
waiting for.
changer?
Let's run the full
Historically, quantum computers were too fragile to be dangerous. If you added more qubits to make a computer stronger, the noise and errors increased until the system collapsed. This was the scaling wall. Willow broke that pattern.
The error rate is still dropping.
For the first
Yes,
time,
qubit count is up.
researchers saw
Let's
that
check the
as they
coherence.
added more
It's stable.
qubits, the
We're on
error
track.
rate actually went down.
The trend
This is called
holding
below threshold error
Error rate is
correction,
below our target
and it's the
threshold.
holy
should
grail
run
of
the
the
next
field.
calibration cycle.
Agreed.
It
This is
proves
promising.
that building
The
a
error rates are trending
massive
down, as you can see.
code-breaking
That's
computer
encouraging. How are the qubits
is
holding
now
up?
just an
Coherence times are
engineering
coherence is
problem,
holding better than our last
not
run.
a physics
Any
mystery.
signs of thermal interference?
Minimal. The gold shielding is doing its job.
Then we're ready to push the qubit
Exactly.
count.
This could be the breakthrough.
To make things even faster, companies are using AI to build these quantum machines. NVIDIA Icing is an AI model designed specifically to handle the tedious manual process of keeping quantum processors stable. It uses AI to identify and fix errors in real time. It's a feedback loop. AI helps build quantum computers, and those quantum computers will eventually train AI at scales we can't even imagine. We're also seeing a breakthrough in the hardware itself with something called Majorana qubits. These are being described as safe boxes for quantum information. So how do we survive a world where the locks don't work? The answer is post-quantum cryptography, or PQC. Since 2016, organizations like NIST have been racing to find mathematical problems that even a quantum computer can't solve. These new methods, like Kyber, are based on lattice-based math. Imagine a grid with 1,000 dimensions. Finding the closest point in that grid is so complex that even a quantum computer gets stuck. The transition is already happening behind the scenes. If you use a modern browser to visit Google, you're likely already using a hybrid key exchange. This combines old-school encryption with new quantum-resistant math. It's a safety net. If one method fails in the future, the other layer still protects your data. This isn't just about security. It's about a massive global power shift. The first organization or nation to master a stable, large-scale quantum computer will have what experts call an asymmetric advantage. It's like having a telescope pointed at the future, while everyone else is in the dark. This is why Google is filing for specialized security clearances and working closer with national security agencies.